This session is just a quick continuation of the mathematical result we're trying to find from the previous session. Remember, we're trying to show that the two different solutions to the Schrödinger equation, UM and UN, that correspond to two different measured energy values, allowed energy values, EM and EN, then those two wave functions, UM and UN, are orthogonal. In other words, the bracket of those two is 0, or alternatively expressed, the overlap integral of those two wave functions is 0. Okay, so we're in the process, about halfway through, in the process of proving that. So we had the two Schrödinger equations, one for UM and the other one for UN, and we multiplied on the left of one of them and multiplied on the left of the other one. Well, don't worry about the details too much. And then we subtracted, and we ended up. So once you subtract, you end up getting this, right? So you notice the V terms, the potential terms cancelled. They cancelled each other up in the subtraction because they were the same. They ended up being the same, which was the reason why we multiplied the first Schrödinger equation by this on the left. Okay, so now once you've got this, the next step is to work on the left-hand side here and integrate. So integrate by parts, and you'll be the things. I should put that as homework. Okay. So fairly routine stuff that doesn't require a lot of thought, that I tend to skip. I tend to ask you to do for homework. So go from this to this. Do that as homework. Okay. So you integrate by parts this integral here, and you're left with something like this. Now, if you make over the limits between, it's one-dimensional problem, so over the x-axis between plus and minus infinity. So the limits, when you do the partial integration, you'll get this term evaluated at the limits x is infinity and minus infinity. Now, assume these wave functions here, UM and UN, assume that they just go to 0 at infinite distance. Okay, so that seems a reasonable assumption. Okay, so assume that they go to nothing as x goes to plus and minus infinity. Well, so that's going to nothing, and this is going to nothing. So assume the left-hand side here just goes to 0, right? All right. So that means that this right-hand side is equal to 0. Well, you now have two possibilities to make this 0. One is that EN and EM are the same. And we assume that UM and UN are different. So if you have two wave functions that give you the same energy, by definition, those wave functions are degenerate. Remember, the definition of degeneracy is when you have two eigenstates that have the same eigenvalue. Now, in this case, the Schrödinger equation is an eigenequation. The wave functions are eigenstates, and the allowed energies are the eigenvalues. Right? So either you have your quantum system is degenerate. You have these two energies are the same, but you have two different eigenvalues, two different wave functions. Okay, so that means if that's the case, you could then perform a measurement, and you wouldn't be able to distinguish between these two states because they give you the same energy. So the assumptions up here would not work. So degeneracy is a bit of a problem in quantum mechanics. You have to handle it a bit differently from the let's say, the mainstream quantum mechanics. So the text glosses over that a little. We'll probably take it up in more advanced texts in, say, first year masters M1. So okay, so either you've got degeneracy. That's one case, or this is zero, which is what we're trying to prove. So in assuming we do not have a degenerate system, right, then the bracket, the overlap integral of these two wave functions that give different values, that we're now assuming that En and Em are different, in other words, non-degenerate, right? So this term here is non-zero, and the left-hand side has to be zero. Therefore, this bracket is zero. Okay, and that's the orthogonality we're trying to prove. So here's your second case. So this is zero, right? In other words, these two wave functions, um or un, or well, same thing, psi m, psi n, are orthogonal. Right? The bracket is nothing, and that means if you do a measurement for this non-degenerate system, then if you get the result for the energy is Em, then the state after the measurement, instead of being well, it'll be this right? If you know the energy of your system is Em, then its corresponding state is psi m. Or if the energy is En, corresponding wave function is psi n. All right. Now let's do that. That's rather general. We didn't specify what V was, the potential was. It dropped out anyway. So let's do a more concrete case now. Let's get my little stool. So the concrete case is, again, we stay in one dimensions, and we're talking about the square well potential, the infinite square well potential, right? And if you go back to chapter 2, lecture 2, we found solutions to that problem for the Schrödinger equation. So the wave function for n, where n is odd, an odd integer. So we had discrete allowed energies for the wave function in the domain where x lies between plus or minus a. The potential was zero. Remember, there's a bit of revision. In this range, x is less than a and larger than minus a. The potential V was zero. Remember. And outside that range, the potential was infinite, impenetrable. And this was the solution we got to the wave function for the Schrödinger equation of this problem, the one-dimensional infinite square well. Okay, we got this term. It's just revision. And these allowed energy values we got took this form: n squared pi squared h bar squared all over h 8 n a squared. And a is the size. Well, half the size of your well, the width of your well. The width of your well is 2a, so ranges from minus a to plus a. Okay? So they're the allowed energies. Right? And your psi function is zero outside that range, because it's infinite, the potential is infinite. It's impenetrable. No wave function can get in it. Right? So it has to be zero outside that range. Right? Now, if this is... that's for a given n. N is an integer, and n ranges, 1, 2, 3, ... Just the ordinary counting numbers, the ordinary positive integers, the natural numbers, if you like, right? Okay, so let's check to see whether, for a given n, we could have psi m and psi n with these values. And we can check if they are, those two different psi functions, wave functions, orthogonal. In other words, is the bracket or the overlap integral, same thing, zero or not? Okay, we can check that. right? So let's calculate the bracket for psi m and psi n. So for psi m, we'll have this will be m and this will be m. Okay. So now the bracket. Remember, you can